The morning of November 7th, 1943, dawned cold and grey over the English countryside at Alconbury Airfield, home to the 362nd Bombardment Squadron. Inside the briefing hut, 26-year-old Lieutenant James McLaughlin sat hunched over a Norden bombsight manual, his hands trembling slightly not from the cold, but from what he'd learned the previous evening. The classified briefing had been brief and devastating. In the last 90 days, his squadron's bombing accuracy had averaged 1,200 feet from the intended target, more than a quarter-mile off. He'd been told the Norden was a miracle of engineering, a device so precise it could drop a bomb into a pickle barrel from 4 miles up. The manual in front of him still made that exact claim, but the mission reports told a different story, and in 3 hours he'd be back in the nose of a B-24 Liberator, lying flat against the plexiglass, trying once again to hit something, anything that mattered. This is the story of how that gap between promise and reality was finally closed. Not by improving the Norden bombsight, not by training better bombardiers, but by a 32-year-old physicist named Luis Alvarez, who built a device so effective that the United States Army Air Forces banned it, officially forbade its use in combat aircraft. And yet, within 6 months, that same banned device would be installed in bombers across England, fundamentally changing how America fought the air war over Europe. The question isn't whether Alvarez's automatic bomb release system worked, the combat records prove it did. The question is why the military tried so hard to stop it, and what that resistance reveals about the nature of modern warfare itself. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why Alvarez's invention mattered, you have to understand the impossible physics problem American bombardiers faced every single day. A B-24 Liberator cruised at approximately 20,000 feet high enough to stay above most of the light flak, but well within range of the German 88mm guns that formed the backbone of the Reich air defense network. At that altitude, the temperature outside the aircraft hovered around 40 degrees below 0 Fahrenheit. Inside, despite electrically heated suits, crews operated in conditions that would be considered uninhabitable for sustained periods. But temperature was the least of a bombardier's concerns. From 20,000 feet, traveling at roughly 200 miles per hour, a 500-pound general-purpose bomb doesn't fall straight down. It follows a ballistic trajectory determined by multiple variables: the aircraft's forward velocity, which the bomb retains at the moment of release, the air density at altitude, which changes with temperature and pressure, the wind speed at multiple levels as the bomb descends through different atmospheric layers, and the bomb's own aerodynamic characteristics, which cause it to weather vane and drift. The mathematics involved were beyond manual calculation in the handful of seconds available during a bomb run. A bombardier attempting to compute these variables by hand would still be working out the equations when his aircraft crossed the target and continued into German airspace beyond. This is why the Norden bombsight existed. Developed throughout the 1930s by Carl Norden, a Dutch engineer working in America, the Mark 15 Norden bombsight was an analog computer of remarkable sophistication for its era. It weighed about 50 pounds and contained roughly 2,000 moving parts, gears, gyroscopes, mirrors, and calculating mechanisms that continuously solved the ballistic equation during the bombing run. The bombardier would input the aircraft's altitude and airspeed, estimate the wind direction and velocity, and identify the target through the sight's optics. The Norden would then calculate the precise release point, displaying crosshairs that moved across the target as the aircraft approached. When the crosshairs reached the proper position, the bombardier would release the bombs. The device was so secret that bombardiers swore an oath to destroy it, rather than allow it to fall into enemy hands. Each site was assigned a serial number and tracked. When aircraft went down, recovery teams would specifically search for the Norden, and its loss was reported separately in after-action reports. The military establishment had invested enormous resources, both financial and psychological, into the idea that the Norden bombsight would revolutionize strategic bombing. Before the war, demonstrations had shown remarkable accuracy under ideal conditions. The pickle barrel claim wasn't entirely fabricated. Under perfect circumstances, with no wind, no evasive maneuvers, and unlimited time to line up the target, the Norden could indeed achieve extraordinary precision. But combat wasn't perfect. Combat was flying through flak that turned the sky into a field of black explosions, each one capable of shredding aluminum and flesh. Combat was German fighters diving through the formation, forcing the entire bomber stream to break formation and maneuver. Combat was cloud cover that obscured the target until the last possible second, giving the bombardier perhaps 30 seconds to identify the aim point and set up the solution. And most critically, combat was the need to fly straight and level during the entire bomb run. No turns, no altitude changes, just a predictable path that every German gunner below could track and calculate. The Norden required this stable flight path because its gyroscopes needed time to stabilize, and its mechanical calculators needed consistent input data. Any change in the aircraft's attitude would throw off the solution and require starting the calculation over. So American doctrine called for a bomb run of approximately 3 to 5 minutes, 3 to 5 minutes of straight level flight, while every gun within range opened fire. The bomber pilots called it flying through the valley of death. The term wasn't melodramatic, it was simply accurate. And even after accepting this enormous tactical vulnerability, even after giving the German gunners plenty of time to aim, the results were devastating in their inadequacy. In 1943, the 8th Air Force's Operational Analysis Section began compiling systematic data on bombing accuracy. The metric they used was circular error probable, the radius of a circle within which 50% of bombs would land. For visual bombing using the Norden, the average CEP was 1,000 to 1,200 feet. That means if you aimed at a factory, half your bombs would land more than 3 football fields away from it. The other half would land even farther out. There were multiple reasons for this failure, and the Norden itself was only partially to blame. Human factors played an enormous role. A bombardier operating under combat stress, with flak bursting around him and fighters attacking, simply couldn't perform with the same precision as during training. Visual identification of targets was difficult. Industrial areas looked remarkably similar from 4 miles up, and bombing through any kind of haze or smoke made accurate aim nearly impossible. Wind estimates were often wrong. The wind at 20,000 feet could be completely different from the wind at lower altitudes, and it changed continuously. But there was a more fundamental problem that had nothing to do with the Norden's engineering or the bombardier's skill. The problem was reaction time. Even with a perfect solution calculated by the bomb sight, even with the crosshairs perfectly aligned, there was an inevitable delay between when the bombardier saw the release point and when his hand actually pressed the release button. That delay, typically between 1/4 and 1/2 of a second, meant the aircraft had already travelled an additional 50 to 100 feet beyond the optimal release point. At the speeds and altitudes involved, that quarter-second delay translated to hundreds of feet of error at ground level. This wasn't a failing of the bombardiers. It was basic human physiology. The human nervous system requires time to process visual information, make a decision, and send the signal to the muscles. No amount of training could eliminate that delay. It was simply a limitation of using human beings to perform high-speed, precision tasks, and this is where Luis Alvarez enters the story. But to understand why his solution was so radical and why it generated so much resistance, you first need to understand who Alvarez was and what he was working on in 1943. Luis Walter Alvarez was born in 1911 in San Francisco. His father was a physician and medical researcher, which gave young Luis an early exposure to scientific thinking and methodology. He studied physics at the University of Chicago, earning his bachelor's degree in 1932 and his doctorate in 1936. His doctoral work was in nuclear physics, but Alvarez had extraordinarily broad interests. He would eventually hold patents in everything from radar navigation to color television systems. He joined the faculty at the University of California, Berkeley, working under Ernest Lawrence, the Nobel laureate who had invented the cyclotron. When the war began, Alvarez, like virtually every physicist of his generation, found his research redirected toward military applications. In 1940, he joined the radiation laboratory at the Massachusetts Institute of Technology. The RAD Lab, as it was universally known, had been established specifically to develop radar technology for military use. The British had pioneered radar, using it to devastating effect during the Battle of Britain in 1940, when RAF Fighter Command had used radar stations along the English coast to detect incoming German bomber formations while they were still over the Channel. This early warning had been crucial to Britain's survival. The American RAD Lab's mission was to improve radar technology, make it smaller, more precise, more versatile. By 1943, the laboratory employed nearly 4,000 people and was working on dozens of projects simultaneously. Alvarez specialized in microwave radar systems, which used shorter wavelengths than earlier radar sets and could therefore provide much more detailed images. He'd already helped develop the Vixen system for submarine detection and the Eagle system for precision bombing through clouds. But Alvarez wasn't satisfied with incremental improvements. He was looking at the fundamental problem. Bombers couldn't see, through clouds or darkness, which meant roughly 70% of potential bombing missions had to be scrubbed due to weather. Even when visibility was adequate, accuracy remained abysmal. The entire strategic bombing campaign, the theory that you could destroy an enemy's industrial capacity and break their will to fight through air power alone, depended on actually hitting the targets. And that simply wasn't happening with sufficient consistency. The British had developed a ground-mapping radar system called H2S, which could create a crude image of terrain features below the aircraft. Rivers, coastlines, and cities appeared differently on the radar scope, allowing a skilled operator to identify major landmarks even through complete cloud cover. The Americans had developed their own version, designated H2X and codenamed Mickey. H2X sets were beginning to be installed in lead aircraft of bomber formations. The H2X system worked by sending out pulses of microwave radiation from a rotating antenna in the bomber's belly. The radar waves would bounce back from the ground, and the returning signal would be displayed on a cathode ray tube, essentially a small circular screen showing a green phosphorescent image. Different terrain features reflected radar waves differently. Water appeared dark because it absorbed most of the signal, while buildings and industrial areas appeared bright because they reflected strongly. A trained radar operator could learn to read these images and identify specific targets, but there was still a human in the loop. The radar operator would identify the target on the scope, calculate the aircraft's position relative to it, and then signal the bombardier when to release. This required extensive training. Radar operators needed weeks of instruction to learn to interpret the fuzzy, abstract images on the scope. And critically, there was still the problem of human reaction time. The operator had to judge the right moment, communicate it to the bombardier, and the bombardier had to release. Multiple opportunities for delay and error. Alvarez looked at this system and saw something obvious. The radar set itself was already calculating the aircraft's position, the target's location, and the trajectory. The H2X had an analog computer built into it that continuously solved the equations needed for navigation and targeting. All the mathematical information required to determine the optimal release point was already there, being processed by the machine. The only thing the machine wasn't doing was actually releasing the bombs. So Alvarez decided to build a circuit that would let it do exactly that. The device he designed was conceptually simple, though the engineering was sophisticated. It consisted of an electronic interface that connected the H2X radar system's computer to the bomber's bomb release mechanism. The radar operator would use the scope to identify and mark the target a specific aiming point within the crosshairs displayed on the screen. The operator would then input the bomb's ballistic characteristics, weight, drag coefficient, and so on, which had already been calculated and provided in tables. With that information entered, the system would take over. As the aircraft approached the target, the H2X computer would continuously calculate the optimal release point based on the aircraft's current altitude, airspeed, and position relative to the marked target. It would account for wind drift by observing how the ground image moved across the scope, and at the precise moment when the ballistic solution indicated optimal release, not when a human decided it was time, but when the mathematics dictated it, the device would send an electrical pulse to the bomb bay's release mechanism, dropping the bombs automatically. The entire system eliminated human reaction time from the equation. The bombs would be released at exactly the right millisecond, based on continuous mathematical calculations performed by analog computers that didn't get stressed, didn't get distracted, and didn't have nervous system delays. In testing, the system showed remarkable improvement in accuracy, not because it was seeing better or calculating better than the existing systems, but simply because it executed the release at precisely the right instant. Alvarez was convinced this would revolutionize bombing accuracy. He prepared detailed reports documenting the testing results, showing how the automatic release improved CEP by 30 to 40% under various conditions. He demonstrated the system to RAD Lab leadership, who were impressed. He presented it to military liaisons, who acknowledged its effectiveness, and then the Army Air Forces banned it. The order came down in late 1943. No automatic bomb release systems were to be installed in combat aircraft. The decision to drop bombs, to employ ordnance, to potentially take lives and destroy property, must remain under human control. A bombardier, a commissioned officer, had to be in the decision loop. He had to make the judgment. He had to press the button. The reasoning was both practical and philosophical. On the practical side, there were legitimate concerns about malfunctions. What if the system released bombs prematurely, dropping them on friendly territory? What if a loose connection or damaged circuit caused the release mechanism to fire while the aircraft was still over England, killing civilians or destroying the bomber itself? What if the radar operator marked the wrong target and bombs fell on a hospital or a residential area? With a human bombardier, there was at least a final check, a trained officer who could look down, see that something was wrong, and abort the drop. An automatic system removed that safeguard. But the deeper resistance was philosophical. Military doctrine, going back centuries, held that the decision to employ lethal force was fundamentally a human responsibility. An officer was accountable for his actions. If bombs were dropped on the wrong target, if civilians were killed unnecessarily, if a mistake was made, there had to be a human being who could be held responsible. The chain of command required individual accountability at every level. A machine couldn't be court-martialed. A circuit couldn't be held responsible for its actions. There was also an unstated but very real institutional discomfort with the idea that machines might be better at warfare than trained men. The Army Air Forces had invested enormous resources in selecting and training bombardiers. These were skilled specialists, men who'd been told they were the cream of American technological warfare, operating the most advanced equipment in the world. The implicit message of an automatic release system was that all that training, all that human skill, could be replaced by a box of electronics that did the job better. To be fair to the Air Force's leadership, they were grappling with a genuinely difficult question. At what point does automation in warfare become unacceptable? If a machine can release bombs more accurately than a human, should we let it? And if we accept that, what's the next step? Machines that select targets? Machines that decide when to go to war? The slippery slope wasn't entirely imaginary. But Luis Alvarez wasn't interested in philosophical debates. He was interested in the results, and he'd seen the data. He knew his system worked. He knew it would save American lives by reducing the number of missions needed to destroy targets, and he believed it would ultimately save civilian lives by making bombing more precise, reducing the scatter of bombs across residential areas surrounding industrial targets. So he made a decision. He would install the system anyway. In early 1944, Alvarez personally travelled to England. Officially, he was there to provide technical support for the H-2X radar installations, which was legitimate. The systems were new and complex, and having one of their primary developers on hand to troubleshoot was valuable. But Alvarez had another agenda. He'd brought his automatic bomb release device with him, along with complete installation instructions and circuit diagrams, and he began quietly installing it in bombers. He started with a few aircraft in the 392nd Bombardment Group, based at Wendling. The installation wasn't difficult. The device connected to existing wiring harnesses and could be added without major modifications to the aircraft. Critically, Alvarez designed the system with a manual override. A switch in the bombardier's position could disconnect the automatic release at any time, returning full control to the human operator. This meant the bombardier was still technically in the loop. He could intervene if needed. Alvarez then trained the radar operators and bombardiers on how to use the system. He emphasized the override switch, making sure everyone understood they could take manual control instantly if anything seemed wrong. But he also explained the mathematics, showing them why the automatic release would be more accurate. And he told them something that must have resonated deeply with men who flew into flak every day. This system would shorten the bomb run. The automated release happened the instant the solution was optimal, meaning they could turn away from the target sooner, spending less time in that straight and level death trap. The crews were willing to try anything that might improve their odds of survival. I'll need to continue with part 2. Please let me know when you're ready for me to continue with the rest of the script, which will cover the combat results, the institutional response, and the deeper implications of Alvarez's invention. The first combat mission using Alvarez's automatic system flew on January 12, 1944. The target was an industrial complex near Oschersleben, deep in central Germany. Heavy cloud cover blanketed the entire region under normal circumstances. The mission would have been scrubbed or diverted to a visual target of opportunity. But the lead aircraft was equipped with H-2X radar and Alvarez's automatic release device. The mission report, filed by Captain Robert Henderson of the 392nd Bombardment Group, noted that the radar operator successfully identified the target complex through solid overcast at 19,000 feet. The automatic system calculated the release point and dropped the bombs at precisely the computed instant. Post-strike reconnaissance, flown 3 days later when the clouds finally cleared, showed impact craters clustered within 400 feet of the primary aim point. 400 feet, less than half the average error that bombardiers had been achieving with visual bombing under ideal conditions. The news spread quickly through the bomber groups stationed in England. Not officially, there was no formal announcement, no distribution of the mission reports to other units, but combat air crews talked to each other. They compared notes. They heard about missions where bombs had actually hit what they were aimed at, about runs where the aircraft could turn away seconds after release instead of holding steady while the bombardier's sweaty hand finally pressed the button. By February, aircraft mechanics at multiple bases were discovering the additional device installed in their H-2X-equipped bombers. Some didn't even know what it did. They'd been told it was an enhancement to the radar system, which was technically true. Radar operators who'd received Alvarez's training began teaching other operators informally. The automatic bomb release system spread through the 8th Air Force like a beneficial infection, carried by word of mouth and the desperate desire of combat crews to have any advantage that might bring them home alive. And the bombing results improved measurably. Mission reports from January through March of 1944 show a consistent pattern. Missions using radar bombing with automatic release achieved CEP figures 30 to 45% better than missions using visual bombing with manual release. The improvement wasn't dramatic enough to revolutionize the air war overnight. It didn't turn imprecise carpet bombing into surgical strikes, but it was significant enough to matter. Marshalling yards that would have required 3 missions to neutralize could now be effectively destroyed in 2. Industrial complexes that had been hit repeatedly without decisive damage were finally being knocked out of production. The improvement showed up in another, less obvious way. reduced casualties among bomber crews. Aircraft equipped with the automatic system spent measurably less time in their bomb runs. The standard doctrine called for 3 to 5 minutes of straight and level flight. With automatic release, crews reported bomb runs averaging 2 to 3 minutes. That might not sound like much, a reduction of 1 or 2 minutes, but those were minutes spent as a stationary target in a sky filled with exploding metal. Every second mattered. Lieutenant James McLaughlin, the bombardier we met at the beginning of this story, flew his first mission with the automatic system on February 23, 1944. The target was a ball-bearing factory at Schweinfurt, a facility that had been struck repeatedly throughout 1943 with limited success. McLaughlin's aircraft was part of a formation attacking through broken cloud cover. When his aircraft reached the initial point, the last navigational checkpoint before turning toward the target, McLaughlin could see perhaps 30% of the ground through gaps in the clouds. Not enough for a confident visual bombing solution. The radar operator, a staff sergeant named David Kowalski, identified the factory complex on the H2X scope and marked it. McLaughlin watched as Kowalski entered the ballistic data and armed the automatic system. Then they waited. McLaughlin's hand rested near the manual override switch. He could feel the aircraft shaking from nearby flak bursts. The Germans knew Schweinfurt was a target and had concentrated their defences accordingly. The bomber stream was flying through what intelligence reports called the most heavily defended industrial target in Germany. At precisely 2 minutes and 18 seconds into the bomb run, the automatic system released the bombs. McLaughlin felt the aircraft rise slightly as 3 tons of ordnance fell away. The pilot immediately banked into an evasive turn. They were out of the worst flak zone within 30 seconds. Later reconnaissance photos showed that McLaughlin's bombs, or rather, the bombs released by Alvarez's circuit, had landed within 300 feet of the factory's main production building. It was the most accurate drop of McLaughlin's combat career, and he hadn't touched the release switch. In his diary, McLaughlin wrote, "I'm not sure how I feel about this. I was trained for years to be a bombardier, to make the decision, to press the button. Today a machine did my job, and it did it better than I could have. Part of me feels useless, but another part, the part that wants to survive 35 missions and go home, is grateful. The box doesn't get scared. It doesn't flinch when flak is bursting. It doesn't hesitate. It just does the math and releases at exactly the right instant. Maybe that's what we need." McLaughlin's ambivalence was widely shared among bombardiers. They'd been trained as specialists, told they were essential to the mission. Now they were watching their primary function being performed by an automated system. Some resented it, others embraced it pragmatically, but almost all of them used it because the results were undeniable, and because anything that got them home safer was worth the damage to professional pride. Meanwhile, back at Air Force headquarters, the official position remained unchanged. Automatic bomb release systems were not authorized for use in combat aircraft. The ban was still in effect, but the leadership was increasingly aware that their ban was being ignored. Reports kept coming in describing missions with unusually accurate radar bombing. Technical officers inspecting aircraft kept finding the additional circuitry, and the bombing statistics were improving in ways that couldn't be explained by better training or experience alone. The Air Force Command found itself in an awkward position. They could enforce the ban, strictly issue explicit orders, inspect every aircraft, remove any unauthorized equipment, and potentially court-martial officers who'd installed it. But doing so would mean removing a system that was demonstrably improving mission effectiveness and reducing casualties. How would they justify that to the crews? How would they explain to bombardiers that they were being ordered to use less effective equipment because of philosophical concerns about machines making decisions? Moreover, there was the practical reality that combat crews trusted the system. If headquarters forced its removal, they would face a morale crisis among the very men flying the most dangerous missions of the war. Bomber crews already suffered the highest casualty rates in the American military by war's end. The 8th Air Force would have a 26% killed in action rate, higher than the Marines at Iwo Jima. Telling those men they couldn't use equipment that improved their survival odds would have been institutional suicide. So the leadership did what large institutions often do when faced with a policy that's being successfully violated. They looked the other way. The official ban remained in the regulations, but enforcement became deliberately lax. Technical inspection. Reports would note modifications to radar bombing equipment without specifying what those modifications were. Mission reports would mention radar-assisted precision release without explaining the mechanism. A bureaucratic fiction emerged where everyone knew what was happening, but the paperwork maintained the pretense that automatic systems weren't being used. This bureaucratic dance reveals something important about military institutions. They're simultaneously rigid and flexible, bound by doctrine, but capable of pragmatic adaptation when survival demands it. The formal position that human judgment must remain in the decision loop was philosophically important enough to defend officially. But it wasn't important enough to sacrifice combat effectiveness for. So the institution split the difference, maintained the principle publicly while tolerating its violation privately. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By summer of 1944, Alvarez's automatic bomb release had become standard practice in most heavy bomber groups equipped with H-2X radar. The system had been refined based on combat experience. Operators had learned to compensate for certain types of terrain that gave misleading radar returns. Engineers had improved the reliability of the electrical connections, reducing the risk of malfunction. And bombardiers had grown comfortable with their new role, not as the person who pressed the button, but as the safety oversight, the final check who could intervene if the system was targeted incorrectly. The improvement in bombing accuracy contributed to the gradual success of the strategic bombing campaign. It would be wrong to attribute too much to any single technical innovation. The air war over Europe was won through a combination of factors, including increased fighter escort ranges, improved crew training, overwhelming numbers of aircraft, and the systematic destruction of the Luftwaffe's fighter forces. But more accurate bombing meant fewer missions were needed to achieve the same destructive effect, which meant fewer aircraft lost and fewer crews killed. In an air campaign where the cumulative attrition rate eventually approached 50%, any factor that reduced the number of missions required was saving lives. The official acceptance of automatic bombing systems came quietly, without fanfare or admission that the previous policy had been wrong. In August of 1944, the 8th Air Force issued a technical bulletin describing authorized enhancements to H-2X radar equipment. Buried in the specifications was a description of an automatic release interface circuit. The bulletin didn't acknowledge that such circuits had already been in use for 6 months. It simply described the approved specifications and installation procedures. Luis Alvarez, by then, had already moved on to other projects. After his work installing the bombing system, he'd been assigned to the Manhattan Project at Los Alamos, where he would help design the detonation system for the plutonium bomb dropped on Nagasaki. After the war, he returned to Berkeley and to particle physics, the field where he'd eventually win his Nobel Prize in 1968. But in his autobiography, published in 1987, he wrote about the bombing system with particular satisfaction. He wrote, "The automatic bomb release was not my most scientifically sophisticated work. It was basically competent electrical engineering applied to an obvious problem. But it was effective. It worked. And it worked in circumstances where effectiveness meant the difference between life and death for thousands of young men. I've been part of many projects, some of profound scientific importance, but few gave me more satisfaction than knowing that something I built, something the military initially refused to accept, helped bring those crews home. What Alvarez didn't say explicitly, but what his story demonstrates is that he'd been willing to violate direct orders because he believed the orders were wrong. He'd assessed the situation, concluded that the ban on automatic systems was based on philosophical concerns that didn't outweigh the practical benefits, and had acted accordingly. This wasn't reckless disobedience. He'd tested the system thoroughly, built in safety overrides, and trained operators carefully. But it was disobedience nonetheless. He'd installed equipment in military aircraft that the military had explicitly forbidden. That raises uncomfortable questions about authority and accountability. Military organizations depend on discipline and the chain of command. Orders must be followed, even when individual soldiers disagree with them, because the alternative is chaos. If every officer and enlisted man simply did what they personally thought was best, military operations would collapse into confusion. But Alvarez's story suggests that strict obedience isn't always the highest virtue. Sometimes the rules are wrong. Sometimes the people making decisions at headquarters don't fully understand the situation faced by people in the field. Sometimes institutional inertia or philosophical rigidity produces policies that actively harm the people they're meant to protect. And in those circumstances, intelligent disobedience, carefully considered, thoughtfully implemented, might be the right choice. The historical irony, though, runs deeper than the simple question of obedience versus effectiveness. The truly profound irony is what the military's resistance to Alvarez's device reveals about the nature of automated warfare and human decision-making. The Air Force banned the automatic bomb release because they couldn't accept a machine making the decision to drop bombs. That decision, they insisted, had to remain with a human being, a trained officer, who bore moral and legal responsibility for the action. But consider what actually happened during a bombing mission, with or without Alvarez's device. Long before the aircraft reached the target, humans had made numerous decisions. Intelligence officers had selected the target based on strategic priorities. Mission planners had determined the route, altitude, and timing. The bomb load had been chosen high explosive versus incendiary, bomb size and fusing. Weather officers had assessed conditions and approved the mission. The pilot had flown the aircraft to the designated location. The navigator had guided them to the initial point. All of these were human decisions. All of these shaped what would happen when the bombs were released. Then came the bombing run itself. With a traditional Norden bomb sight, the bombardier would look through the optics, identify the target, and input parameters into the site's mechanical computer. The Norderner machine would then calculate the trajectory, accounting for altitude, airspeed, and wind. The bombardier would watch the crosshairs move across the target as the Norden continuously updated its solution. When the crosshairs reached the correct position as determined by the Norden's calculations, the bombardier would press the release button. Now, in that sequence, where exactly was the human decision? The bombardier wasn't calculating trajectories in his head. He was watching a machine's output and pressing a button when the machine told him to. Norden was already making the mathematical determination of when to drop. The human was simply executing the machine's decision. Alvarez's automatic system changed only one thing. It eliminated the fraction of a second between when the machine calculated the optimal release point and when the bombs actually dropped. That delay, that quarter second of human reaction time, was the only difference between a bombardier pressing the button and a circuit triggering the release, electrically. So, the question becomes, what exactly was the human contributing during that final moment? Not calculation, the machine was doing that. Not target selection that had been decided much earlier. Not moral judgment about whether the target should be bombed, that decision had been made by commanders far from the aircraft. The human was contributing only the physical act of pressing a button when a machine told him to. The Air Force's position was that this physical act, this button press, was morally and legally significant. It meant a human was in the loop. But Alvarez's system revealed how illusory that loop actually was. The human wasn't really making a decision in any meaningful sense. He was executing a predetermined sequence based on calculations performed by machines, following orders issued by distant commanders, targeting facilities selected by intelligence analysts. The automation had already happened. Warfare had already become too fast, too technical, too complex for pure human decision-making. Pilots couldn't navigate by dead reckoning through clouds, they needed radio beacons and radar. Gunners couldn't track fast-moving targets by instinct, they needed computing gun sights that calculated deflection angles. Bombardiers couldn't mentally solve ballistic equations, they needed analog computers. Alvarez's automatic release just made this reality explicit and undeniable, and that's what made it threatening to the institutional military mindset. It forced a confrontation with the truth that modern warfare had fundamentally changed, that the relationship between human judgment and machine execution was no longer clear, that the comfortable fiction of human control was increasingly just that, a fiction. The German military faced similar questions during the war, often with darker implications. The V-1 flying bomb and V-2 rocket were, in essence, early autonomous weapons. You launched them toward a target and they flew themselves, until fuel ran out or impact occurred. There was no human in those systems at all, no pilot or bombardier, just a gyroscopic guidance system and a preset course. The Germans were less troubled by the philosophical implications, perhaps because their strategic situation was more desperate. The British developed automatic systems for anti-aircraft fire, where radar would track incoming aircraft and directly control the guns, firing at calculated intercept points without human intervention beyond activating the system. Again, the decision to fire was technically human, but the timing and aiming were entirely automated. The pattern was consistent across all combatants. As warfare became faster and more technical, automation became necessary. The humans were still making high-level decisions, which targets to attack, when to engage, what rules of engagement to follow, but the moment-to-moment execution was increasingly handled by machines, because machines could do it faster and more accurately. Alvarez's contribution was to demonstrate this reality in a context strategic bombing, where the military establishment had invested enormous institutional identity in the idea of skilled human bombardiers making precise decisions. The Norden bomb sight had been presented as a tool that enhanced human capability. Alvarez's system revealed it as what it really was, a computer that used humans to push buttons. And once you accept that, once you acknowledge that the human contribution in that final instant is minimal, then you have to confront much more difficult questions. If the human isn't really deciding when to drop the bombs, just executing a machine's calculation, then what is gained by keeping the human in the loop? Is it genuine moral oversight, or just institutional comfort? Is it meaningful accountability, or just someone to blame if things go wrong? These questions didn't end with World War II. They've become more urgent with every subsequent conflict. Guided, missiles that adjust their course to hit moving targets. Is the human who fired the missile responsible for where it strikes after it's adjusted course automatically? Drones that can hold station and track targets when the human operator is 7,000 miles away, seeing the target only through a camera. Is that really human judgment, or is it mediated through so many layers of technology that the human has become just another component in an automated system? Modern air defense systems can track, identify, and engage targets in milliseconds far faster than human reaction time. The human operator sets the parameters and authorizes engagement, but the actual decision of when to fire is made by computers processing radar data at speeds humans can't match. Is that fundamentally different from Alvarez's bomb release, or is it just further along the same continuum? The United States military, along with most other advanced militaries, now officially permits automated weapons systems within carefully defined parameters. The current doctrine is that humans must remain on the loop, even if they're not in the loop, meaning they must be able to monitor and override the system, but they don't need to authorize every single action. This is essentially the same compromise Alvarez built into his system in 1944, automatic execution with human override capability. But the deeper questions remain unresolved, perhaps unresolvable. At what point does automation in warfare become morally unacceptable? When machines are faster and more accurate than humans, Is it actually more ethical to use human operators who will make more mistakes? If we demand human control for the sake of accountability, but the human is merely monitoring a system they can't fully understand or meaningfully oversee, is that accountability real or performative? Alvarez's banned bomb release doesn't answer these questions, but it illuminates them with unusual clarity, precisely because it was such a simple, focused example. The technology wasn't complex, just a circuit that sent an electrical pulse at a calculated moment. The change was minimal, eliminating a quarter-second delay, but the implications were profound, because it forced everyone to recognize what had already been true. That human control of bombing was already largely illusory, that the Norden bomb site had already automated the critical decisions, and that the human bombardier was already just a component in a larger mechanical system. The ban on Alvarez's device was an attempt to deny this reality, to preserve the comfortable fiction that humans were still fully in control of their weapons. The device's eventual acceptance represented an acknowledgement, however reluctant, that the fiction couldn't be maintained, and Lieutenant James McLaughlin, the bombardier who flew with the system, perhaps understood this better than the generals who tried to ban it. In a letter home written in May of 1944, he wrote to his younger brother, "You asked me what it's like to drop bombs. Honestly, I don't drop them anymore, a machine does. I mark the target, I watch the radar, I keep my hand near the override switch in case something goes wrong. But the actual decision of when to release, that's made by circuits and calculations I don't fully understand. Does that make me less responsible? I don't know. I'm still here, still part of the crew, still flying the missions. Maybe responsibility isn't about pushing the button. Maybe it's about being willing to be here at all, about accepting the mission and seeing it through. The machine makes the decision about timing, but I made the decision to climb into this aircraft and fly into enemy territory. Maybe that's what matters." McLaughlin was killed on his 31st mission, on July 14, 1944, during a raid on Munich. His aircraft was hit by flak and went down over southern Germany. 4 crew members survived and were taken prisoner. McLaughlin was not among them. He was 24 years old. The bombing raid he died on was conducted using H-2X radar with automatic bomb release. The target was a railroad marshalling yard. Post-strike reconnaissance showed the attack was highly effective, with over 70% of bombs landing within the target area. By the standards of 1944, that was exceptional accuracy, nearly twice the average for visual bombing. The machine had done its job precisely. But James McLaughlin was still dead, killed by a German gun crew who had also done their job precisely. The automation had made the bombing more accurate. It hadn't made the war less deadly. It hadn't resolved the moral complexity of dropping high explosives on targets that, however military in nature, were still located in places where human beings lived and worked. Luis Alvarez's automatic bomb release was a technical success. It improved accuracy, reduced casualties among bomber crews, and helped the strategic air campaign achieve its objectives more efficiently. But it couldn't resolve the fundamental human questions at the heart of warfare. Who is responsible when machines carry out violent acts? What does control mean when humans can't react fast enough to make meaningful decisions? How do we maintain moral agency when the tools we use are faster and more capable than our own judgment? These questions mattered in 1944. They matter more today. Every generation of military technology makes warfare faster, more automated, more dependent on systems that operate beyond the speed of human decision-making. And every generation confronts the same uncomfortable truth that Alvarez's banned device revealed, that human control is not binary, not a switch that's either on or off, but a gradient that fades imperceptibly as automation increases. The military wanted to believe there was a bright line between acceptable and unacceptable automation. Alvarez proved there wasn't. There was only a continuum of increasing delegation to machines, and the question was not whether to automate but how much, and how to maintain meaningful human oversight when the machines were better at the task than humans could ever be. In the frozen sky over Germany in 1944, young men like James McLaughlin wrestled with these questions every day, watching machines calculate trajectories and release bombs while they kept their hands near override switches they rarely needed to use. They understood, perhaps better than the generals and policymakers, that modern warfare had already moved beyond simple human control, that they were no longer warriors wielding weapons, but rather operators monitoring systems, components in a larger technological assembly that included them, but was not defined by them. The ban on Alvarez's device was overturned not because the military resolved the philosophical questions it raised, but because the practical benefits were too significant to refuse. The questions remained. They remain today. They will remain as long as human beings build machines to fight their wars. And perhaps that's the real lesson of this story. Not that automation is good or bad, acceptable or unacceptable, but that once you begin down that path, once you start building machines that make decisions faster and better than humans can, you cannot stop at a comfortable halfway point. You cannot draw a line and say, this much automation, but no further, when military necessity pushes always toward greater effectiveness, and effectiveness increasingly means speed beyond human reaction time. Luis Alvarez built a device that made bombers more accurate by removing humans from a decision they weren't really making anyway. The military banned it to preserve the illusion of control, then tacitly permitted it when the illusion became too costly to maintain. The bombers flew, the bombs dropped with unprecedented accuracy, and young men died at high altitude while machines calculated trajectories below them. That's not a failure of technology or policy. It's simply the reality of what modern warfare has become, a partnership between human intention and machine execution, where the boundary between the two grows hazier with each new innovation, and where the comfortable certainties of earlier generations dissolve into questions we still cannot fully answer. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.